You're looking to be genuinely well-informed, right? To cut through the hype, understand what really matters, but without drowning in information overload.
Exactly.
Well, that's precisely what we do here on the Deep Dive. Think of this as your curated briefing. We take a whole stack of sources and pull out the crucial insights for you.
And today, we're diving into a collection of material all about something that could genuinely reshape our future. Quantum technology.
Quantum technologies. Yeah, it sounds like something straight out of sci-fi, but it's becoming very real, very fast. We're going to hit 5 key areas that sort of make up this whole quantum landscape.
Right. We've got quantum computing, or QC.
Then post-quantum cryptography, PQC.
Quantum sensors, QS.
The quantum internet, QI.
And finally, quantum key distribution, which is QKD.
And our mission really is to give you a clear picture. Where do these things stand today? Are they commercially viable? What are the actual benefits? And importantly, what are the risks, the challenges?
Precisely. We want to understand how these technologies are all connected, their potential, and, the hurdles we still need to overcome.
Okay, let's dive right in then, starting with quantum computing. QC.
Right.
Forget your laptop or phone. This is a completely different way of calculating things.
It's a fundamental shift. It uses the rules of quantum mechanics, the really weird ones, to tackle problems that are just, impossible for even our best supercomputers today.
Okay, so how does it actually work? What are the core ideas?
Well, at the heart of it, you've got a few key concepts. First, forget bits, the zeros and ones we know. Quantum computers use qubits.
Qubits, okay.
And here's where it gets interesting. A qubit can be in a superposition.
Meaning?
Meaning it's like being both 0 and 1 at the very same time. Think of a spinning coin before it lands. It's not heads, not tails. It's sort of both.
Uh-huh.
Mathematically, we can write that state like alpha 0, the Lero wrangle, plus alpha 1, 1 wrangle. Those alpha symbols basically tell you the probability, the chance, it'll end up as 0 or 1 when you finally look at it.
So it's probabilistic, not definite until you measure.
Exactly. And this both-at-once ability means the information capacity just explodes. A few dozen qubits can represent, theoretically, more states than there are atoms in the universe.
Wow. Okay. That's a lot.
It is. Then there's entanglement.
Ah, yes. The spooky action at a distance.
That's the one. It's this incredibly strange link between 2 or more qubits. If you measure one, you instantly know the state of the other no matter how far apart they are. It's like they're connected by some invisible thread.
It still blows my mind every time I hear about it. Instant connection.
It's a fundamental property of quantum mechanics. And then there's quantum interference.
Interference, like waves.
Kind of. Quantum algorithms are designed really cleverly so that the probability paths leading to the correct answer reinforce each other. They get stronger.
Okay.
While the paths leading to the wrong answers cancel each other out. They interfere destructively.
So you boost the right signal and cancel the noise, basically.
That's a good way to put it. And finally, when you measure a qubit, that whole superposition collapses. Poof. It becomes a definite 0 or a definite 1.
According to those probabilities you mentioned earlier.
Exactly. Which is why you often have to run a quantum calculation many, many times to build up the statistics and be confident in the answer.
Right. It's not just one shot, get the answer. It's about finding the pattern.
Precisely. And companies like IBM, Google, D-Wave, they've been pioneers in taking this, really abstract theory and actually building physical machines.
And we are seeing real hardware now. It's not just equations on a blackboard anymore. What's the current state of play? How mature is this tech?
We've definitely moved beyond pure theory. We have tangible hardware, though it's still very much early days.
Uh-huh.
A really big moment was back in 2019. Google claimed quantum supremacy with their Sycamore processor.
Right, I remember that. Huge headlines.
They solved a very specific, kind of obscure mathematical problem in minutes. Something that, they argued, would take the world's most powerful classical supercomputers thousands of years. Some later analyses, comparing to the Frontier supercomputer, put it at maybe 47 years, but still,
Right.
A massive difference.
An incredible speed up, yeah. But it wasn't a practical problem, was it? Not something useful in the real world.
No, absolutely not. It was a proof of principle, a huge achievement, for sure. But it highlighted that the utility of these current machines is still quite limited.
So where are we now, mostly?
We're firmly in what's called the NICE-2 era, noisy intermediate scale quantum.
Noisy and intermediate scale. Okay.
Yeah, it means these machines have a limited number of qubits, maybe tens, maybe a few hundred, and crucially, they're noisy. They're incredibly sensitive to their environment.
What does noisy mean in this context?
It means things like heat, vibration, stray electromagnetic field can easily disrupt the delicate quantum states. This is called decoherence. It causes errors in the calculation.
Ah, okay, so they're fragile.
Extremely. The big long-term goal is FTQC, fault-tolerant quantum computing.
Fault-tolerant, meaning they can correct these errors.
Exactly. But that's a massive leap. We're talking potentially millions of these noisy physical qubits working together, using complex error correction codes just to create maybe a few thousand stable, reliable, logical qubits.
Millions for thousands. That sounds like a monumental engineering challenge.
Oh, it absolutely is.
Yep.
And there isn't just one way to build a qubit. Researchers are exploring lots of different physical approaches.
Like what?
Well, you've got superconducting circuits. IBM and Google use these. They're fast, but very sensitive to noise and need to be kept incredibly cold, near absolute zero.
Right. Big refrigerators.
Yep. Then you have trapped ions. These hold their quantum state for longer, they're more stable, but generally slower to operate. Companies like Quantinuum focus here.
Okay.
Photonics uses particles of light, photons, as qubits. Big advantage. They can potentially operate at room temperature and leverage existing fiber optic tech. But building reliable quantum gates with photons is tricky. There are neutral atoms held by lasers, which look promising for scaling up. Diamond nitrogen vacancy NV centers are interesting. They can work at room temperature too, maybe good for sensors or memory. Topological qubits are theoretically very noise resistant, a huge plus, but proving incredibly hard to actually build and demonstrate.
So lots of different horses in this race.
Definitely. And then you have quantum annealers, like D-Wave's machines. They're different, designed specifically for optimization problems, not general-purpose quantum computing.
So no clear winner yet on the best way to build a qubit.
Not at all. Each approach has its pros and cons: speed, stability, temperature needs, how easy they are to scale up. A huge amount of research right now is focused on just making better qubits more stable ones.
And the error correction piece sounds critical too.
Absolutely essential. Quantum error correction, QEC, is key to getting beyond this NISQ stage. Without it, the errors just overwhelm the computation as you add more qubits or run longer algorithms.
Got it. Are these machines accessible at all, or just locked away in labs?
Increasingly, yes. We're seeing more access through cloud platforms. IBM, Google, Amazon, Microsoft. They offer access to their quantum hardware, which lets more people experiment and develop algorithms.
Okay, so the big question. When will these things actually be commercially useful? When will they start making a real impact?
That's the billion-dollar question, isn't it? Predicting the timeline is really tough.
Yeah.
If you look back, the predictions for quantum computing have often been, more than 10 years away for a long time. Gartner tracked this.
Always just over the horizon.
Pretty much. But perspectives are starting to shift. McKinsey, for instance, they're projecting a market of around $131 billion by 2040. That's up massively from their 2023 estimate of $9 billion.
A huge jump. What are experts saying about fault tolerance?
McKinsey's 2023 survey found that about 72% of experts expect we'll see full fault tolerance by 2035. The rest think it'll be after 2040.
But there are definitely contrasting views out there.
Oh, for sure. NVIDIA's CEO, Jensen Huang, suggested maybe 15, 20 years plus, much more cautious. But then you have D-Wave, with their annealers, arguing they already provide value for specific optimization tasks.
So near-term niche applications might be possible.
Yes, especially using hybrid classical quantum approaches, or those specialized annealers. We're seeing pilot projects and things like logistics optimization. Denso, Pattison used D-Wave for that. Financial modeling, BBVA. Bankia, materials and drug discovery, IBM's worked with Moderna.
But these aren't widespread uses yet.
No. They tend to be premium solutions, offering maybe incremental improvements on very hard problems. And the cost for these early proof of concepts can be significant, around $350,000 for some D-Wave projects, for example.
So widespread impact really depends on
those fault-tolerant machines, the FTQC systems with thousands of stable logical qubits.
And the timelines for those?
Roadmaps from companies like IBM and Quantinuum suggest maybe the mid-2030s is when we might start seeing them emerge. But it's still R&D.
And there's a global race aspect to this too, right?
Absolutely. Huge international rivalry, particularly the U.S. focusing heavily on computing, China investing massively in quantum communications. And there's enormous funding pouring in from both governments and private investors. Gov funding is estimated to be roughly double private funding globally right now.
Okay, so assuming we get these powerful, fault-tolerant machines eventually, what are the game-changing benefits we're talking about? Which industries will feel it most?
The potential is just immense. First, sheer processing speed and the ability to analyze massive, complex data sets. Remember the Sycamore example. Extrapolate that capability to real-world data. We're generating unimaginable amounts of data. Frost and Sullivan predicted 181 zettabytes by 2025. QC could help us make sense of it incredibly quickly.
Finding patterns hidden in that noise.
Exactly. Then think about chemistry, material science, pharma. Quantum computers could simulate molecular interactions with incredible accuracy that could revolutionize how we discover new materials. Lighter alloys for aerospace, better catalysts, more efficient batteries, new drugs, faster, cheaper discovery.
That alone sounds transformative.
It really is. In finance, much more sophisticated modeling for portfolios, risk analysis, fraud detection, faster algorithmic trading.
AI and machine learning.
Quantum ML is a huge potential area. Could mean faster training for complex models, potentially improved accuracy.
Logistics, supply chains.
Big optimization potential there too. Better scheduling, routing, huge efficiency gains possible.
Cryptography. You mentioned it's a threat, but also an enabler.
Yeah, it forces the move to PQC and QKD, but a quantum internet could enable new quantum cryptographic protocols too.
Even things like environmental science.
Potentially, yes. Modeling complex ecological systems, climate change impacts, solving network problems related to biodiversity.
And architecture, engineering, construction, AEC.
Yes, applications there too. Optimizing complex project designs, analyzing material performance under stress, simulating structural integrity for mega projects, urban planning simulations, potentially synergies with AI for things like optimizing tendering or risk management.
Wow. It really does seem like almost every field could be touched by this eventually.
That's the potential, yes.
But there have to be risks, big hurdles. What are the major ones?
Absolutely. On the purely technical side, the fundamental challenges remain huge. Decoherence and noise, just keeping the qubits stable enough to compute reliably, that sensitivity is inherent.
Yay, the fragility.
Then qubit stability and scalability. How do you actually engineer systems with millions of high-quality qubits that work together perfectly? It's an enormous engineering lift.
And the error correction needed for that?
Quantum error correction is vital, but it comes at a huge overhead cost in terms of the number of physical qubits needed per logical qubit. Very resource-intensive. Even seemingly basic things like preparing the qubits in the exact starting state you want, state preparation, and then accurately measuring the result at the end, those still have efficiency and accuracy challenges.
So these aren't minor issues. They're fundamental science and engineering problems still needing major breakthroughs.
Correct. And beyond the tech hurdles, the security implications are probably the most immediate worry for many.
The code-breaking potential.
Exactly. The fact that a large enough fault-tolerant quantum computer could run Shor's algorithm and break the public key cryptography we rely on today, RSA, ECC, that's huge.
That underpins secure websites, digital signatures, so much.
Everything. Online banking, secure communications, software updates. This leads to the harvest now, decrypt later HNDL threat.
Explain that again.
Adversaries could be capturing and storing encrypted data today, data that needs to stay secret for years or decades, government secrets, health records, intellectual property. And they're just waiting until they get access to a quantum computer powerful enough to decrypt it all later.
Oof, that's worrying.
It is. And because our digital world is so hyper-connected, breaking this foundational crypto could cause systemic vulnerability across the board.
And the fix moving to quantum-resistant crypto, that's not simple either.
No, the transition challenges are significant. Migrating entire systems to new cryptographic standards is complex, it takes a long time, it's expensive, and there's always the risk of introducing new vulnerabilities during the process if it's not done carefully.
So even the solution carries risk. What's the key takeaway for, say, a CISO right now?
Act now. Don't wait. Start inventorying where you use cryptography, understand your data sensitivity and required lifetimes, and begin planning the migration to quantum-resistant solutions. Even if fault-tolerant QCs are years away, the HNDL threat is real today for long-lived data, and the migration takes years. Proactive preparation is absolutely essential.
That leads us perfectly into our next big topic, post-quantum cryptography, or PQC. If quantum computers are the threat, PQC is meant to be the shield, right?
Exactly. PQC is all about developing new cryptographic algorithms, ones that run on classical computers we have today, but that are designed to be secure against attacks in both classical computers and future quantum computers.
And the need comes directly from that threat we just discussed, Shor's algorithm breaking RSA and ECC?
Precisely. That vulnerability impacts HTTPS secure websites, digital signatures, verifying software or documents, encrypted email, secure financial transactions. The list goes on. PQC aims to provide replacements for these vulnerable algorithms.
And these new PQC algorithms, they're based on different kinds of math problems.
That's right. Problems that we currently believe are hard for both classical and quantum computers to solve. Things like lattice-based cryptography, code-based, hash-based signatures, multivariate polynomial cryptography, different mathematical foundations.
And the urgency, again, is driven by that HNDL threat and the long time it takes to switch everything over.
Yes. If data needs to be secure for 10, 20, 30 years, it's potentially vulnerable now if it's encrypted with current methods. And migrating complex systems, testing, ensuring compatibility, that's easily a decade-long process for many organizations, maybe longer.
So what's being done to standardize these new methods? I know NIST has been heavily involved.
Yes, the U.S. National Institute of Standards and Technology, NIST, has been leading a major international effort. They started a public competition back in 2016.
A competition?
Yeah, inviting cryptographers worldwide to submit candidate algorithms, then subjecting them to intense scrutiny and analysis over multiple rounds. It's been a very open and collaborative process.
And have they chosen the winners? Are there standards now?
Yes, as of August 2024, they announced the first set of finalized standards. FIPS 203 standardizes ML-Chem, which you might know as Crystal's Kyber. That's primarily for key establishment, replacing things like RSA or ECC for encryption.
Okay, so that's for setting up secure connections. What about digital signatures?
For signatures, there's FIPS 204, which is ML-DSA, or Crystal's dilithium, and FIPS 205 standardizes SLH-DSA, also known as FITS plus PIC. FIPS plus is a hash-based signature scheme which has different properties.
So we have official replacements ready to go now.
We have the first batch, yes. And NIST is still working. They've indicated Falcon is likely next for standardization as another signature scheme, FIPS 206. And they've also selected HQC as another key establishment mechanism, kind of a backup, expected to be standardized by 2027.
It sounds like a thorough process. Has it been smooth sailing?
Not entirely. It's iterative. Some algorithms that look promising early on, like Psyche, were actually broken during the process, which, is actually a good thing. It shows the analysis is working.
Better to find flaws now than later.
Absolutely. It really underscores the need for ongoing research and what's called cryptographic agility.
Yeah.
The ability for systems to be updated or switched to different cryptographic algorithms relatively easily if vulnerabilities are found in the future. Designing systems with that flexibility is crucial.
So when can we expect to see these PQC algorithms actually being used? When is it commercially viable?
Well, since PQC algorithms run on classical computers, viability is really tied to the standards being finalized and vendors integrating them. With the first FIPS standards out, we're already starting to see products and libraries incorporating Crystal's Kyber and dilithium.
So it's happening now?
The integration is starting, yes. But widespread adoption across the entire internet and all software. That will take time. Remember, experts predict cryptographically relevant quantum computers, CRQCs, might appear within 10-20 years. Some, like Gartner, warn current crypto could be unsafe even by 2029, maybe broken by 2034.
So there's a deadline, potentially.
A potential one, yes. And history tells us these migrations take a long time. Migrating to modern public key infrastructure took almost 2 decades, so planning needs to start immediately.
Are governments pushing this?
Definitely. The U.S. NSA has mandated federal systems transition by 2035. The White House issued NSM-10 in 2022, urging preparations. Gartner flagged PQC as a top strategic tech trend for 2025.
What's the advice for organizations during this transition?
A key recommendation is often a hybrid approach.
Hybrid.
Meaning, for a time, use both a traditional algorithm, like RSA or ECC, and a new PQC algorithm together. So an attacker would need to break both to compromise the communication. It provides redundancy and helps with compatibility during the rollout.
Okay. And what steps should companies be taking now?
Develop a quantum readiness roadmap. Conduct a crypto inventory, figure out where all your current cryptography is being used. Assess the risks based on data sensitivity and lifetime. Start talking to your vendors about their PQC plans, and begin pilot projects to test PQC implementations in your own environment.
It sounds like a major undertaking.
It is. Gartner predicts that 1 in 5 organizations will actually be budgeting for quantum threats by 2026. It's becoming a concrete planning item.
So what are the main benefits of making this huge effort? Why go through the pain of migrating?
The biggest benefit is future-proofing data security. It's about protecting sensitive information against that harvest now, decrypt later threat. It's about ensuring business continuity, preventing a future scenario where past communications suddenly become decrypted. It's about meeting regulatory compliance, preserving customer trust, and building overall organizational resilience. Ultimately, it's about maintaining confidentiality, integrity, and authenticity in the quantum era.
But it's not all smooth sailing. What are the risks and challenges in the transition itself?
There are definitely significant challenges. One big area is performance and efficiency.
How so?
Many PQC algorithms, especially the lattice-based ones like Kyber and dilithium, have larger key sizes and signature sizes compared to RSA and ECC.
Okay, what does that mean practically?
It can impact network bandwidth, sending more data. It needs more storage space. It can increase processing time, especially on smaller resource-constrained devices like in the Internet of Things, IoT. Some algorithms might also require more computational power, affecting energy consumption or necessitating hardware upgrades.
So potential performance hits? What else?
Implementation complexity and compatibility. Integrating these new algorithms into existing systems and protocols can be difficult. Legacy systems might not be easily upgradable. And many systems weren't built with that cryptographic agility we mentioned, making it hard to swap algorithms.
Right. And the algorithms themselves are still relatively new.
Yes, algorithm maturity and security auditing is another factor. While they've undergone intense scrutiny in the NIST process, they haven't had the decades of real-world testing that RSA and ECC have. There's always a possibility of finding new implementation vulnerabilities or side-channel attacks. And we can't fully test them against large quantum computers yet because those don't exist.
Makes sense. What about the cost?
Cost and resource allocation will be substantial. The White House estimated the cost just for migrating U.S. federal systems could be around $7.1 billion by 2035. It requires significant investment in planning, software development, hardware upgrades, testing, and personnel training.
That's a big number. Any other hurdles?
Supply chain and vendor coordination is key. Organizations rely on vendors for hardware and software, so those vendors need to provide PQC-compliant products in a timely manner. And finally, organizational readiness and misconceptions. There's a risk that some organizations might underestimate the threat or the complexity of the transition and delay action, which could be very risky.
So it's a complex balancing act, a race against a future threat, dealing with practical challenges today. Okay, let's shift gears. Let's talk about another area where quantum mechanics is making waves, quantum sensors.
Right, quantum sensors, or QS. This is about using quantum phenomena to measure things with unprecedented precision and sensitivity.
Better than classical sensors.
Potentially much better. They can detect incredibly faint signals or tiny changes in things like magnetic fields, gravity, time, or temperature signals that are simply invisible to traditional sensors.
How do they achieve that? What's the fundamental principle?
It boils down to exploiting the fact that quantum states are extremely sensitive to their environment. You prepare a quantum system, maybe atoms, maybe photons, maybe specific defects in diamond, in a very precise initial state.
Okay.
Then you let it interact with whatever you want to measure, say, a magnetic field or acceleration. That interaction subtly changes the quantum state. Finally, you measure the final quantum state very precisely. By comparing the final state to the initial state, you can figure out the strength of the interaction and thus the value of the quantity you're measuring with incredible accuracy.
So the quantum system acts like a tiny, super-sensitive probe.
Exactly. They can push beyond the standard quantum limit or shot noise limit that fundamentally limits classical sensors, potentially reaching towards the ultimate precision allowed by physics, the Heisenberg limit.
Wow. Okay. What kinds of quantum sensors are we talking about? Is it just one type?
Oh, no, it's a really diverse field. There are many different types, using different quantum principles.
Like?
Well, maybe the most famous are atomic clocks. They use the incredibly stable frequencies of atomic transitions to keep time with astonishing accuracy. Essential for GPS, telecom networks, fundamental physics experiments, even geodesy, measuring the Earth's shape and gravity field.
Okay, super precise clocks. What else?
Magnetometers. Sensors for magnetic fields. There are several quantum types. NV centers in diamond allow for very sensitive measurements, even at the nanoscale, potentially useful for medical imaging or material science. Squades are based on superconductivity and are extremely sensitive, used in medicine and geophysics, but need cryogenic cooling. Optically pumped magnetometers, OPMs, use lasers and atomic vapor, offering high sensitivity without extreme cooling, promising for brain imaging.
So better ways to measure magnet fields. Keep going.
Then you have sensors for motion and gravity. Gravimeters, accelerometers, gyroscopes. Many of these use atom interferometry, where you manipulate clouds of ultra-cold atoms with lasers. They offer incredible sensitivity and stability for things like inertial navigation without GPS, resource exploration, monitoring volcanoes or structures.
Navigation without GPS, that sounds huge.
It's a major driver. There's also quantum imaging, using quantum properties of light like photon statistics entanglement or squeezed light to get better resolution or sensitivity than classical imaging. Applications in medical imaging, microscopy, defense, maybe even better LiDAR.
Interesting. What about biology or medicine directly?
Quantum biosensors. These aim to use quantum effects, maybe combined with plasmonics, or using quantum dots, or entanglement to detect biological molecules like proteins or DNA with extreme sensitivity and specificity. Huge potential for early disease diagnosis, environmental monitoring, drug discovery.
And I saw something about exceptional point sensors. Sounds exotic.
Yeah, that's a newer area based on concepts from non-Hermitian quantum mechanics. The idea is that systems near these exceptional points can exhibit dramatically enhanced sensitivity to tiny changes. Still early stage, but potential for things like refractive index or magnetic field sensing.
It's a real zoo of different sensor types. Are they getting smaller or more practical?
That's a major trend. Miniaturization and chip-scale integration are key. We already have chip-scale atomic clocks, CSX. Researchers are working hard on chip-scale gravimeters, magnetometers, etc. Getting these sophisticated physics packages onto small, robust chips is seen as crucial for mass-market adoption, much like MEMS technology revolutionized classical sensors.
So when do we expect these to move from the lab into widespread use? What's the commercial picture?
It's definitely happening, but at different paces for different sensor types. The market is growing. IDTech's forecasts it reaching maybe $2.2 billion by 2045. McKinsey's more aggressive, predicting $6 billion by 2040.
So significant growth expected.
Yes. We're seeing a clear transition from university research labs to commercial products. Some technologies like squid eddies or certain atomic clocks have been commercial for a while. Quantum dots are used in some infrared cameras, but newer types are now emerging from startups, university spinouts, and established tech companies getting into the game.
Are there specific applications driving this?
National initiatives, like the UK's quantum technology hubs, are certainly helping. Navigation is definitely seen as a potentially huge mass-market driver chip-scale sensors for autonomous vehicles, drones, smartphones. That could be massive if the manufacturing challenges for these complex physics packages can be overcome at scale.
So manufacturing is a bottleneck.
Scaling up production while maintaining performance and reducing cost is definitely a challenge.
Yeah.
Often, development follows a solution pull model.
Meaning?
Industry identifies a critical need like reliable navigation where GPS is denied, or better medical imaging, or more efficient resource mapping, and that pulls the technology development forward.
And there's a whole ecosystem around this. Components and stuff.
Absolutely. A robust supply chain for specialized components is vital. Ultra-pure materials, specific lasers, advanced photonics, cryogenics for some types, sophisticated control electronics. That supply chain itself is a significant secondary market opportunity.
Okay, let's talk benefits. Sector by sector. What could quantum sensors enable?
In healthcare, think revolutionary biosensors for detecting diseases much earlier. Nanoscale MRI using NV centers for incredibly detailed cellular imaging. Better brain imaging, MD-MCG with OPMs or NV centers, higher resolution medical imaging like OCT.
Huge potential there. Navigation.
Navigation and timing. As we said, GPS-independent inertial navigation using quantum accelerometers and gyroscopes, a game changer. Ultra-stable, compact atomic clocks for better timing synchronization.
Resource exploration.
Resource exploration and geophysics. Highly sensitive gravimeters and magnetometers could make finding mineral deposits, oil and gas reserves, or groundwater much more efficient. Also, better monitoring of geological hazards like volcanoes or subsidence.
Defense and security.
Defense and security. Again, GPS-denied navigation is critical. Also, enhanced detection of stealthy objects through seismic or magnetic anomalies. Potentially very sensitive RF sensors.
Industrial uses. Environment.
Industrial applications and environmental monitoring. Non-destructive testing of materials or structures with higher precision. Predictive maintenance based on subtle vibration changes. Better detection of tiny gas leaks. Tracking pollutants. Monitoring crop health. Climate research benefits from more precise measurement.
And fundamental science.
Fundamental research. These sensors are becoming essential tools for pushing the frontiers of physics, searching for dark matter, testing fundamental symmetries, detecting gravitational waves.
That GPS-denied navigation capability really does seem like a standout application.
It's potentially transformative for autonomous systems, military operations, even things like indoor navigation.
But like all these quantum techs, there must be downsides. What are the risks or limitations of quantum sensors?
Definitely. A major one is fragility and environmental sensitivity.
We heard that with quantum computers too.
Yes. Many quantum sensors are very sensitive to vibrations, temperature changes, stray electromagnetic fields. They often need significant isolation vacuum chambers, cryogenic cooling for some, magnetic shielding. This adds to their size, weight, power consumption, and cost, what's often called swap.
Size, weight, and power, right.
So size, weight, and power itself is a challenge. Current high-performance systems can be bulky and power-hungry. Making them compact, low power, and high performance is tough.
What else?
Complexity and cost. These are often intricate systems, sometimes handcrafted in labs. They require skilled personnel to operate and maintain. Manufacturing is complex, driving up costs. A high-end quantum gravimeter might cost $500,000, for example.
It limits adoption.
For sure. Scalability and production challenges are related to precise fabrication techniques, sourcing specialized materials, standardizing manufacturing processes.
Standardization sounds important.
Yes, calibration and standardization is currently lacking for many types. It's hard to compare performance between different sensors or integrate them easily without agreed-upon standards.
Is classical sensor tech standing still?
Not at all. Competition with advancing classical sensors is real. Quantum sensors need to offer a clear, significant advantage to justify their often higher cost and complexity. Classical sensors are constantly improving too.
And for sensors collecting environmental data, any specific concerns?
Data governance is an emerging issue, especially for large sensor networks. Questions around data interoperability, access, ethical use, potential biases in how data is collected or interpreted, and preventing misuse.
So huge potential, but practical hurdles around robustness, cost, scale, and integration still need work. Okay, let's move to the network. The quantum internet. Sounds even more futuristic.
The quantum internet, or QI. Yes, it's a really ambitious vision. It's about building a global network that uses quantum mechanics entanglement, superposition, to do things completely impossible in today's classical internet.
More than just faster downloads, then.
Oh, much more. It's about enabling fundamentally new forms of communication and distributed computation.
Okay, conceptually, how would it work? What are the building blocks?
Well, instead of classical bits, it transmits qubits. The absolute cornerstone is entanglement, creating linked pairs of qubits and distributing them across the network.
Right, that spooky connection.
That's the key resource. But remember the no cloning theorem. You can't just copy a qubit like a classical bit. That means you can't use standard amplifiers or repeaters like we do in classical fiber optics.
Ah, okay. So how do you send quantum information over long distances?
That's where decoherence also bites you. The quantum state degrades over distance and time. So the network needs several key components. You have the quantum nodes or end users. These could be quantum computers, sensors, or just communication devices. They're connected by quantum channels, optical fiber, free space laser links, maybe even satellite links. To overcome distance limits, you need quantum repeaters. These are complex devices that use techniques like entanglement swapping and purification, often needing quantum memory to store qubits temporarily to extend the range of entanglement.
Quantum repeaters sound critical then.
Absolutely essential for a large-scale terrestrial QI. You also need reliable quantum memory, ways to transduce qubits between different physical forms, like from a stationary qubit in a computer to a flying photon for communication. And coordinating all this quantum stuff likely requires a parallel classical control network.
So it's a hybrid system in practice.
Likely, yes. The architecture involves distributing entanglement, either directly or using that swapping technique. Probably using a layered protocol stack, conceptually similar to the classical internet's TCP/IP stack, but designed for quantum information.
And you mentioned hardware is key here, especially those repeaters and memories.
Absolutely critical. QI development is very much hardware-centric right now. The software and protocols are important, but they can't overcome the fundamental physics limitations without breakthroughs in repeaters and memory. And, importantly, that classical control plane needs to be secure too, likely using PQC to protect it from quantum attacks.
Where are we with building this? Is it just theory, or are there actual networks?
It's definitely in the early experimental stages. There's a lot of research globally, and several small-scale test beds are up and running.
But not a real quantum internet yet.
Not in the sense of a versatile multi-purpose network. Most current quantum networks are either focused solely on quantum key distribution, QKD, or they're limited testbeds for exploring basic entanglement distribution over relatively short distances. The leap to a true QI really depends on those repeater and memory breakthroughs.
Can you give some examples of these test beds?
Sure. China has made significant progress, including a 4,600-kilometer integrated space-to-ground network using their MISHA satellite, mainly for QKD. The UK has the UKQN testbed. In the US, there's the Chicago Quantum Exchange Network, and the Department of Energy has a blueprint for a national QI, with projects like IQNet connecting national labs. The EU has the EuroQCI initiative focused on QKD across Europe, and the Quantum Internet Alliance, QIA, working on entanglement distribution. Canada, Singapore, Italy, Japan, lots of activity worldwide.
So lots of projects. Are there timelines or roadmaps?
Yes, various national strategies and research initiatives have laid out roadmaps. The U.S. DOE blueprint from 2020 outlined a staged approach, aiming for a prototype QI within a decade. The EU's QIC roadmap aimed for high technology readiness levels by 2025 and the EuroQCI operational by 2027. Canada's strategy also had short, medium, and long-term goals. But the general consensus among experts seems to be that a large-scale network based on quantum repeaters is likely still more than a decade away.
Is there significant funding behind this?
Yes, substantial investment globally. The market for QI components and services is projected to grow rapidly, potentially reaching over $8 billion by 2030. R&D spending in 23 was estimated over $3 billion globally, dominated by the US, China, and EU. China's total investment since 2016 is thought to exceed $15 billion. The U.S. National Quantum Initiative allocated $1.2 billion. The EU's quantum flagship is $1 billion over 10 years.
Big money. Who do you expect will build the first ones?
Like the early classical internet, initial deployments are likely to be government-driven, focused on national security and critical infrastructure needs.
Okay, so if we get there, what are the revolutionary benefits? What can a QI do that the classical internet can't?
The potential is huge. Ultra-secure communication is a big one, enabled by quantum key distribution, QKD, which we'll discuss more next. Also, potentially tamper-proof data transmission using entanglement and advanced cryptographic protocols like secure multi-party computation, blind quantum computing, secure voting, even certified data deletion.
Beyond just security.
Yes. Distributed quantum computing.
Right.
Imagine linking multiple QCs together via the QI to create a much more powerful computational resource. Or providing secure remote access to quantum computers, quantum as a service. That's a key milestone in the U.S. DOE plan.
Wow, linking quantum computers. What else?
Networked quantum sensing, using entanglement distributed over the QI to enhance the precision of sensor networks. Think creating continent-sized telescopes by linking optical clocks, or building improved GPS-like positioning systems, or distributed environmental monitoring with unprecedented sensitivity.
So using the network itself is part of the sensor.
Exactly. Other possibilities include potentially faster communication for certain tasks, more efficient distributed data processing, things like quantum leader election protocols, or incredibly precise time synchronization across the network. The real power comes from distributing entanglement, enabling this collaborative quantum advantage, where networked, maybe imperfect quantum devices can achieve things together that they couldn't alone.
That sounds incredibly powerful, but the hurdles must be enormous too. What are the main roadblocks?
They are significant. Decoherence, that fundamental fragility of quantum states, is always a top challenge.
Right.
Scalability. Going from small lab setups with a few nodes to national or global networks is a massive engineering leap.
And the repeaters?
Quantum repeaters. Absolutely crucial for long-distance terrestrial QI, because you can't just amplify quantum signals.
Yeah.
Building efficient high-fidelity repeaters is arguably the major technological bottleneck right now. If that proves too hard, we might rely more heavily on satellites, but satellites have their own limitations, line-of-sight requirements, bandwidth limits, vulnerability.
What about storing the quantum information?
Quantum memory. You need reliable ways to store qubits with high fidelity and long coherence times, especially for repeaters and synchronization. Still a major research challenge.
Other issues?
Cost, definitely. The specialized hardware is extremely expensive currently. Basic hardware limitations in generating entangled photons efficiently, minimizing losses in fiber, building robust qubits. We need entirely new software and protocols designed for quantum communication. Figuring out how to integrate the QI with our existing classical internet, they'll likely need to coexist. And ensuring the security of the network components themselves, like the repeaters, against physical tampering or side-channel attacks.
given all that, what's a realistic expectation for the near future?
The high cost and complexity suggests that the first iterations of the QI might be specialized, high-security networks for government or critical infrastructure, rather than a ubiquitous public network like today's internet. We might see tiered access develop.
A long road ahead, but with potentially revolutionary payoffs. Okay, finally, let's focus on quantum key distribution, QKD. You said this is the most mature quantum communication tech.
That's right. QKD is the most developed application, and it's specifically focused on one task, allowing two parties to establish a shared, secret cryptographic key with extremely high security. Security that's theoretically resistant to all adversaries, including those with quantum computers.
Okay, how does it achieve that level of security? What's the principle?
It uses quantum mechanics to guarantee that the key exchange is secure. The basic idea is to encode bits of the key onto quantum states, usually individual photons, using properties like their polarization or phase. A common protocol is BB84. Alice sends photons encoded in one of several randomly chosen bases, say horizontal, vertical, or diagonal. Bob measures them, also choosing his measurement basis randomly.
Okay.
The key physics principles are, first, the no cloning theorem. An eavesdropper, Eve, can't just copy the photon in its quantum state without disturbing it.
Right, no perfect copies.
Second, measurement disturbs the system. If Eve tries to intercept and measure a photon, especially if she guesses the wrong basis, she will inevitably introduce detectable errors or changes in the quantum state.
So any eavesdropping leaves a trace.
Theoretically, yes. After Alice has sent a stream of photons, she and Bob communicate over a regular, authenticated classical channel like the normal internet. They compare notes on which basis they use for a subset of the photons. Where they use the same basis, they should have the same bit value. Where they use different bases, the results are discarded.
So they filter out the mismatched ones?
Right. Then they estimate the error rate on the bits they kept. If the error rate is suspiciously high, they assume Eve was listening in and discard the entire key attempt. If the error rate is low enough, attributable to noise in the channel, they proceed with error correction to fix the discrepancies and privacy amplification to distill a shorter but truly secret shared key.
And the goal is unconditional security.
That's the theoretical aim security, based purely on the laws of physics, not on assumptions about computational difficulty. But, and this is crucial, the security of the real-world implementation depends heavily on the hardware being perfect, the protocols being implemented correctly, and very importantly, the security of that classical authentication step.
Ah, so there's still a classical component that needs securing.
Yes. Alice and Bob need to be sure they're talking to each other on that classical channel, not to Eve pretending to be Bob. That authentication usually relies on pre-shared secrets or potentially PQC algorithms.
Okay, so QKD security is physics-based for the key exchange itself, while PQC is math-based computational security.
Exactly. QKD aims for provable security against interception during exchange. PQC aims for computational security against decryption later. They address slightly different aspects, and that reliance on classical authentication in QKD can sometimes bring computational assumptions back into the picture.
How mature is QKD technology in practice? Is it being used?
It's definitely the most mature of the quantum communication technologies. Commercial off-the-shelf QKD systems are available from several vendors, companies like ID Quantique, Toshiba, Magic Q, Quintessence Labs, Quantum C-Tech in China, Cuno Labs in India, Quantum Exchange.
So you can actually buy this stuff?
Yes. It's been demonstrated over hundreds of kilometers in fiber and thousands via satellite link, like China's Midges. The market was estimated at over $1.1 billion in 2023 and is projected to grow significantly, maybe to $8.6 billion by 2032.
Are there real-world deployments? Who's using it?
We are seeing deployments, though still somewhat niche. Government and defense agencies are key users. Financial services, JP Morgan, HSBC, SoftBank have run experiments. Critical infrastructure operators, healthcare institutions securing sensitive patient data, data centers linking facilities, telecom providers, research networks. There was even a demonstration securing communications for a G20 summit. And some exploration in securing vehicle-to-everything, V2X, communications for autonomous driving.
But it's not mainstream yet.
No, adoption is still limited, mostly driven by organizations with extremely high security needs and the budget for the specialized infrastructure. Broader adoption really hinges on lowering costs, making integration easier, and overcoming the distance limits.
You mentioned satellite QKD is important.
Yes, it's strategically significant because it bypasses the signal loss issues inherent in long optical fibers. Satellites could potentially create global QKD networks, relaying keys between ground stations continents apart. China's Misha satellite really demonstrated this potential.
Okay, what are the main benefits? Why choose QKD?
The core benefit is quantum-safe security for the key exchange itself, based on physics. Then there's the unique ability of eavesdropping detection in real time. If someone tries to intercept the key exchange, the system flags it.
That's a big difference from classical crypto.
Huge. This directly counters the harvest now, decrypt later threat for the key itself. If the key exchange is compromised, you know immediately and don't use the key. So it's great for securing high-value data and critical infrastructure where future decryption is unacceptable. The value proposition is the theoretical impossibility of covert interception of the key versus the computational infeasibility of breaking the encryption later with PQC.
Makes sense, but what are the limitations? It sounds like there must be some significant ones.
There definitely are. A major one is distance constraints.
Why is distance a problem?
Photons get lost or absorbed in optical fiber. The loss increases exponentially with distance, and you can't use standard optical amplifiers because they destroy the quantum state due to the no-cloning theorem. This limits direct point-to-point QKD links over fiber to maybe a few hundred kilometers maximum in practice. The key generation rate also drops dramatically with distance.
So how do you go further?
Currently, you need trusted relays, essentially intermediate nodes that decrypt and re-encrypt the key. But each relay needs to be physically secure, which undermines the end-to-end security guarantee. The long-term hope is functional quantum repeaters, but as we discussed, those are still under development.
Okay, distance is a big one. What else?
Special purpose equipment and infrastructure. QKD needs dedicated hardware, specialized photon sources, and detectors. It typically requires dedicated fiber optic channels or clear line of sight for free space links. You can't just run it as software on existing networks.
And cost.
High implementation and operational costs are a factor related to the specialized hardware and infrastructure.
You mentioned authentication is needed too.
Yes, QKD only secures the key exchange itself. It's a partial solution requiring authentication. You still need a secure way, ideally PQC or pre-shared keys, to authenticate the classical channel used for key sifting and reconciliation. Without secure authentication, Eve could potentially impersonate Bob to Alice, a man-in-the-middle attack.
Are there security concerns with the devices themselves?
Yes, security and validation challenges. Real-world QKD devices aren't perfect. Imperfections can open up side-channel vulnerabilities where Eve might glean information about the key without directly measuring the photons. Fully validating the security of a complex QKD system is very difficult.
What about denial of service?
That's a risk. Because QKD is designed to detect disturbances, an attacker could potentially just disrupt the quantum channel, e.g. by shining bright light into the fiber, to prevent keys from being established, a denial of service attack.
Any other limitations?
It's generally incompatible with existing wireless networks that use radio frequencies. There's a talent shortage of people skilled in deploying and managing these systems. And, as mentioned, there's some skepticism from security agencies like the NSA, who currently favor PQC for broad use due to QKD's limitations and complexities.
So QKD seems powerful for specific niche uses, but maybe not a universal replacement for PQC in the near term?
That seems to be the consensus view. It might remain niche for high-security point-to-point links for a while, but the R&D driving QKD, advancing photonics, detectors, quantum device engineering is incredibly valuable for other quantum technologies too.
Okay, that covers the 5 main areas. It's clear they're not developing in isolation. Let's talk about how they connect the synergies, dependencies, maybe even competition between them.
Absolutely, they're deeply intertwined. Quantum computing QC is a really interesting case because it acts as both a threat and an enabler.
How so?
Well, the threat of QC breaking current crypto, RSA ECC via Shor's algorithm, is the primary driver for developing both PQC and QKD. The whole field of quantum-resistant cryptography exists because of the potential power of future QCs. The timeline for when we might get cryptographically relevant quantum computers, VRQCs, is absolutely critical for PQC-QKD adoption strategies.
Right. And how is QC an enabler?
It's a catalyst. QC itself could potentially help design and analyze new PQC algorithms, or simulate QKD protocols. It could be crucial for designing better quantum sensors, simulating new materials or sensor configurations, processing the complex data they generate. And QC is a key potential application for a future quantum internet enabling distributed QC and also potentially helping design network components, routing algorithms, error correction for the QI itself.
So the threat is also a tool. Interesting. How do PQC and QKD compare head-to-head, and do they complement each other?
They offer different approaches. PQC security based on computational hardness, runs on classical hardware, scalable using existing infrastructure, good for broad protection, signatures, encryption everywhere, but no inherent eavesdropping detection. QKD security based on physics principles for key exchange, detects eavesdropping during exchange, protects against HNDL for the key itself, but needs special hardware. Distance limited, without repeaters relays, higher cost, mainly for key exchange on specific links.
So potentially complementary.
Very likely. You can see PQC used for general-purpose security, authenticating connections, signing software, etc., while QKD is deployed on particularly critical links maybe between data centers, government sites, financial institutions, where the absolute maximum assurance for the key exchange is needed. And there's a direct synergy. PQC can be used to provide the secure classical authentication needed for QKD.
Right. National strategies might push one over the other, too.
Potentially, yes. Depending on priorities, perceived threats, and industrial capabilities, different countries might emphasize PQC or QKD development and deployment differently.
Okay, what about the quantum internet? How does it enable QC and QS?
The QI is envisioned as the platform for things like distributed quantum computing. Linking multiple QCs via the QI could create a machine far more powerful than any single one. That's a major goal, like US Dewey Milestone 3. It also enables networked quantum sensors. Entanglement distributed over the QI could allow sensor arrays to achieve sensitivities impossible. Otherwise, like long baseline telescopes, better GPS, synchronized clocks, distributed environmental monitoring.
But the QI needs to be pretty advanced to support that.
Yes. It requires high-fidelity entanglement distribution, good quantum memory, low-latency scalable repeaters. These applications really leverage the quantum nature of the network, not just using it as a secure pipe.
And how do QC and QI help quantum sensors? Can they boost sensor capabilities?
Definitely. QC for sensor data processing. Imagine using quantum algorithms for advanced signal processing, noise filtering, or pattern recognition on the huge data sets coming from quantum sensor networks. Or using QC to simulate and design better sensor materials or devices. QI for networked and secure sensing. The QI could enable distributed sensing using entanglement between sensors. It could also provide ultra-secure channels using QKD or other quantum crypto for transmitting sensitive sensor data.
Could there be feedback loops?
Potentially.
Yeah.
You could imagine a scenario where the QI enables real-time analysis of sensor data by a remote QC, which then adjusts the sensor parameters via the QI for optimal performance. It creates this positive feedback loop. Better QI enables better QC/QS, which drives demand for more capable QI.
It really underscores the interdependencies. A breakthrough in one area could really accelerate others, or a delay could hold things back.
Exactly. If QC advances rapidly, that increases the urgency for PQC/QKD adoption, but might also speed up sensor design. If progress on quantum repeaters stalls, it limits terrestrial QI and QKD range, pushing focus toward satellites or maybe delaying distributed QC. Successful PQC standardization and adoption is crucial for securing the classical parts of QKD and QI systems. Advances in quantum sensors might provide better components, like photon sources or detectors, for QI and QC, and also drive demand for the secure comms and advanced processing they enable. Conversely, if sensors remain too costly or fragile, it might dampen enthusiasm or investment in the wider ecosystem. Strategic initiatives often recognize these links, trying to foster progress across the board.
Okay, let's try and wrap this up. Bringing it all together, what's the snapshot of quantum technologies right now?
It's a really dynamic picture. Quantum computing. Immense long-term potential, but fault tolerance is still a significant way off. Post-quantum cryptography. The immediate, broad defense against the future quantum threat, with the critical need for adoption now. Quantum sensors, already seeing near-term commercial impact in niche areas with strong potential for growth. The quantum internet, a longer-term vision requiring fundamental breakthroughs in repeaters and memory. And quantum key distribution, a mature niche solution for ultra-high security key exchange, available today, but with limitations.
And the key takeaway is just how interconnected they all are. Progress, or lack of it, really ripples through the whole ecosystem.
Absolutely. You can't really look at any one of them in isolation.
Hmm.
The next decade feels absolutely critical. We need to see widespread PQC adoption happening. We need quantum sensors to scale and become more cost-effective. And we need continued fundamental R&D breakthroughs to make fault-tolerant QC, a functional QI, and more versatile QKD a reality.
It really makes you wonder, doesn't it? How might progress in, say, materials science for better qubits unexpectedly accelerate quantum sensing? Or could a delay in quantum repeaters actually push PQC adoption faster? It leaves you pondering the surprising twists and turns that might shape the timeline for a truly quantum-enabled future. Something for you to think about. Thanks so much for taking this deep dive with us today.